All right, folks, last worksheet, the last part of the worksheet for gas laws for the review. This happens to be number 6. Right. As we notice, what's going on is we are changing a gas from a certain temperature and pressure to STP. So that means we have something changing. So we're going to use our combined gas law, which is P1V1 over T1 is P2V2 over T2. Right? And we have milliliters, and we have kPAs, and we have Celsius. We know we have to change the Celsius. All right, so let's say 98.7 Celsius plus 273, and that's going to give us 371.7 Kelvin. Now, what about everything else? Well, so long as we're consistent in our units, it doesn't matter what our units are, aside from Kelvin. Kelvin must be Kelvin. So our initial pressure is 220.0 kilopascals, and our initial volume is 23.5 milliliters. We're doing this in milliliters, not in liters, folks. You have to be careful with that. And our temperature is 371.7 Kelvin. So long as we keep our units the same, we're okay. So what's our pressure? Well, our standard temperature and pressure is 0 degrees Celsius. And 1 atmosphere of pressure. So 1 atmosphere of pressure is 101.325 kilopascals. We know that because we know what 1 atmosphere is equal to. And we're trying to figure out our milliliters. And our temperature is going to be 0 Celsius, which is 273 Kelvin. All right. So I multiply these things over here, and I divide by what's left. So I get 220.0 kPa. Times 23.5 milliliters times 273 Kelvin, and I divide that by 371.7 Kelvin, and I divide it by 101.325 kilopascals. So I'm going to get rid of my kilopascals, I'm going to get rid of my Kelvin, I'll be left with milliliters as my final units, and I get 37.5 milliliters as my final answer to number 6. All right, how about number 7? What's the density of oxygen gas at 40 degrees Celsius, Find grams per milliliter. It gives you a hint. All right, so we have to figure out grams per milliliter. All right, so it says assume you have a given amount of grams. You choose. Well, let's choose 1 mole, just because that's easy, which is 32 grams of oxygen, and then convert to a volume. Okay, so let's convert this to a volume. Well, 40 degrees Celsius is 40 plus 273, and 40 plus 273 is 313 Kelvin, and 615 millimeters of mercury. Let's go ahead and convert that to atmospheres. 615 millimeters of mercury. Because we're going to want to use PivNert here. 760 millimeters of mercury in 1 atmosphere. So that's going to be less than 1 atmosphere, and that number is going to give us 0.809 atmospheres. All right, let's see. So now if we're going to use PivNert, what we have to do, we know how many grams we have. It's 1 mole of gas. So let's go ahead and figure out our using PivNert. Let's see, PV equals nRT. What do we have to figure out? Well, we know N, obviously we know R, we know our temperature, we know our pressure. What we don't know is volume, so we have to solve for volume. That way we can do density. Volume is going to be nRT over P, which is equal to, let's see, our number of moles is 1 mole. That was easy. 0.0821 liters, atmospheres, moles, Kelvin. That's moles. And we're going to multiply by temperature, which is 313 Kelvin. We're going to divide by our pressure, which is 0.8092 atmospheres. Let's see, we have atmospheres and atmospheres. We have moles and moles and Kelvin. We're left with liters. How cool. So this comes out to be 31.756 liters. Now notice this is in liters. All right, and we're looking for grams per milliliter. All right, so we know we have 32 grams. Let's see, we have 32 grams, and if we're doing it per milliliter, if this is liters, then milliliters, we simply multiply by 1,000. So that's 31,756 milliliters. So if we do that, we get about 0.001. In fact, we do get 0.00101 grams per milliliter. In other words, not very dense at all, which is what we'd expect. All right. How about number 8? Number 8, let's see. What is the temperature of a gas that has a volume of this, and it was initially at G? This looks like we have something changing, doesn't it? So let's go and see what we have. We have 555 milliliters, 43.5 atmospheres, 20 degrees Celsius. Well, let's change that. 20 plus 273 is equal to 293 Kelvin. And we have a volume here of 885 milliliters and 2204 torr. All right, well, that means we're going to have to do a little bit of conversion here because we've got this in atmospheres and we've got this in torr. And let's see. By the way, in your on the sheet you have, I believe that's listed as 0.555 liters. Sorry, so 0.555 liters is going to be 555 milliliters. That's my bad. When I copied it wrong. All right, so let's say that we want to do this. Okay, I'm one of those people who likes to do things in atmospheres. So let's take 2204, and that's in torr, which is the same as millimeters of mercury. So that means there's 760 torr in 1 atmosphere. And if I multiply that out, I actually get a nice round figure of 2.900 atmospheres. All right, so now what I should be able to do is P1 V1 over T1 equals P2 V2 over T2, which means I have my initial pressure, let's see, pressure, which is 43.5, oh no, initial. This is my initial stuff over here. My initial stuff is 2.900 ATMs. My initial volume is 855 milliliters. So long as we're consistent and use milliliters or liters, it doesn't matter. I'm going to use milliliters just because it's easy. And my temperature originally is 293 Kelvin. And I'm trying to figure out my new temperature, which is T2. And my new pressure is 43.5 atmospheres. Wow, that's a big number compared to 2.9. And our milliliters are 555 milliliters. All right, so what I need to do is I need to multiply these guys and divide by what's left. So I take 293 Kelvin and I multiply by 43.5 ATMs. And I multiply by 555 milliliters, and I divide by what's left, which is 2.900 ATMs, and I divide by 885 milliliters, and notice my milliliters cancel and my ATMs cancel, leaving me with the Kelvin temperature, which is exactly what I want, which is 2750 Kelvin. That's a huge number. I have to subtract 273, remember, to go back to Celsius. And so I end up with 2483. But I've only got 3 sig figs up here, so I'm going to end up with taking this to 2480 degrees Celsius. That's my final temperature. That is absolutely huge. All right, number 9. This is the last one. We're saying at 298 Kelvin, oxygen travels at 1,200 miles per hour. What's the speed of helium at the same temperature? All right, well, we do have to remember we're dealing with oxygen, which is O2. So that's going to weigh 32 grams. And if we look up helium, that's 4.003 grams per mole. And we know that oxygen has a particular speed of 1,200 miles an hour. That's pretty fast. All right, so we have to remember that our rate of A over the rate of B is equal to the square root of the molar mass of the inverse, which is B, divided by the square root of the molar mass of A. All right, well, let's assume that A is helium, and let's assume that B is O2. So that means this is going to be O2 up here, and this is going to be helium here. All right, so what do we know? Well, we know that the molar mass of B, which is oxygen, is 32, and the molar mass of A is 4.003, and we know that the rate of oxygen is 1,200 miles an hour. So, using cross multiplication, multiplying these, dividing by what's left, I should be able to come up with the rate of helium. So I take 1,200 miles per hour, I multiply by the square root of the molar mass of B, which is 32, and I divide by what's left, which is the square root of 4.003. Right, when I plug all of that into my calculator, I get 3,393, but because of sig figs, I'll knock it down to 3,400 miles per hour. So that is the speed of helium at the same temperature as oxygen. Okay? That's it, folks. That's it for the review. If you have questions, please see us in class. We'll be happy to help you with anything. And have a great day. We'll see you soon. Bye.